All right, so we've been calculating limits. So as x approaches some number, what is the limit based on the function of that number? So we've done some practice with that, and now we are ready to look at one of the most important questions that defines calculus. And that is, how do you define the slope of a curve? All right, so I know if I have a curve, and if I just look at something that we know, let's look at this quadratic function. And if I want to find the slope of a curve, let's say I have a point here, I need another point to find the slope. So if I pick another point that's on the curve and then find the slope between those 2 points, that would be finding the slope of a secant line, because a secant line is going between 2 points in a curve. But in calculus, what we're doing is we're looking for the slope of that one particular point. Okay, and if we have a line that hits a curve at one point, we call that a tangent line. All right, so in example 1, it says to how do you find the slope of the function f of x equals x squared. All right, so if I were to say I want to find the slope by using these 2 points, let's say this is x and over here I have c, I would take, the y value here would be f of x, and this would be f of c. Whatever the x value is, plug it into the function, you get the y value, which is the same as f of x. So I'm going to have this equation. Now we know that the slope of this line is the change in the y values over the change in the x values. So if I want to find the slope of the secant line, I need the change in the y values, so I have f of x minus f of c over the change in the x values, which would just be x minus c. Okay, so if I have some number here, I would just plug that value in to the function and I would be able to calculate. So this is pretty generic here. But if we do have a value, well, let's look down here. Slope of a secant line, that's what we just found here. And this is the same as the average rate of change. That's what slope is. Between 2 points. Okay, so that's pretty much what we have here. So the slope of the secant equals f of x minus f of c over x minus c. But if we want to find the slope of the tangent line, okay, now this is at one point, so this would be the instantaneous rate of change. And that happens at 1 point. Now, if something's happening at 1 point, one thing that we can do is to get a more exact is we can kind of slide this point closer and find the rate of change between the 2 points and get it even closer, and getting it even closer to where the second point is actually on top of the first point. Okay, so to do that, we're going to use limits. So to find the slope of the tangent line, or the instantaneous rate of change, we have the limit as x approaches some number, and that number is getting closer and closer and closer to x, where it almost is x, where f of x minus f of c over x minus c. Okay, so this one we have 2 points and we can calculate the value. This one, the 2 points are the same. Okay, so what happens here is when we plug in c for x, we're going to get a 0 on the denominator, and we're going to have to do some simplifying. But down on the bottom it says if the slope of a tangent line exists, the equation of the tangent line is y minus f of c, we can call this y1, equals the slope of the tangent line times x minus c, or x1. So this is just point slope form. Okay, y minus y1 slope times x minus x1. So this is really just algebra. Okay, so we're using algebra to do the calculus. So on the next page, on example 2, it says to find an equation of a tangent line to the graph at f of x equals x squared divided by 4 at the point 1/4. All right, so find the equation of a tangent line. So the tangent line means we want to find the slope at x equals 1, because that's the x value that we have here. Okay, so if I plug in, or I use my formula, now I want to find the slope at x equals 1, so in my formula x is going to approach 1, and I want f of x minus f of c over x minus c. So if I plug these values in now, I have the limit as x approaches 1 of f of x. Now f of x is x squared divided by 4 minus f of c. So if I plug in 1 here, this tells me what the value is. So that would be 1/4. And I can just see 1 squared is 1 divided by 4 is 1/4 over x minus c, which is 1. So what I can do here is if I find this limit and I plug it in, I notice I'm going to get a 0 over 0. So I'm going to have to do some simplifying. So the first thing I'm going to do is factor out this 1/4 on the top. X squared minus 1, x minus 1. And now this x squared minus 1 can be it is the difference of squares. So I'm going to have the limit, of x approaches 1. And then I have 1/4 times x plus 1 times x minus 1, and that's divided by x minus 1. Now I can cancel my x minus 1's. So this gives me the limit as x approaches 1 of 1/4 times x plus 1. So if I now plug in 1, I'm going to have 1 plus 1 is 2 times 1/4, which is 1/2. So this is the slope of the tangent line. But here they're asking us to find the equation of the tangent line. So we're just going to plug this in. Find the equation. I just have y minus y1 equals the slope times x minus x1. I just calculated the slope, and I can say that this is x1 and y1. So I'm just going to use point slope form. So I have y minus y1 is 1/4 equals the slope, which is 1/2, times x minus x1, which is 1. That's the equation of the slope of the tangent line of that function. Now, if we look at what we're doing, this is really just algebra 1, finding the slope of a line and writing it in point slope form. Okay, relating it to calculus, the slope of the tangent line is called a derivative. And I think calculus has two main parts. One of them is derivatives, and the other is integrals. I can't say that word, but the derivative is the equation of, or the slope of the tangent line. The integral is the opposite of that, or undoing a tangent line, the slope, and going back to the original function. Okay, so they're just inverses of each other. But a derivative is the slope of a tangent line. Which is the instantaneous speed at some point. Or instantaneous rate of change, which is, in physics, we would call that speed. All right, so here we have f prime. So this is the derivative of f at some number c. So we use this f prime, or, the little apostrophe up there, f prime of c equals the limit as x approaches c of f of x minus f of c over x minus c. So we've just done all that. So here in example 3, this is real calculus talk here. It says to find the derivative. Okay, same question, different name. Find the slope of the tangent line at a specific point on this function. All right, so we're going to find the limit as x approaches 2, because it says find f prime at 2 of f of x minus f of 2 over x minus 2. Now, just for calculating sake, I'm going to do some calculating over here. If I want to find f of 2, I just got to plug that into the function. So f of 2 is 2 times 2 squared minus 5 times 2. So this is 8 minus 10, so that's negative 2. So now if I replace f of x with the function, I have the limit as x approaches 2. F of x is 2x squared minus 5x minus f of 2, which is negative 2, so that'd be plus 2 right here, over x minus 2. So I'm going to write this as plus 2. So I know that if I plug in 2, I'm going to get a 0 on the denominator, and that's just by design. All right, so I'm always, most likely I'm going to have a 0 on the denominator. So I'm going to need to factor this. So I have the limit as x approaches 2. Now, thinking ahead, I should probably be able to cancel an x minus 2 on top and bottom. So I'm going to try and factor out an x minus 2, and let's see what I would have. So what would I put here times x to get 2x squared? So that would be 2x. And then I have, let's see, what do I multiply by negative 2 to get positive 2? And that would be a minus 1. And if I just double check with my FOIL here, this is 2x squared. Minus 4x minus 1x is minus 5x. And then negative 1 times negative 2 is positive 2. So that works. I'm going to cancel. So the slope of the tangent line, or the derivative as x approaches 2, is 2x minus 1. If I plug in 2 now, 2 times 2 is 4, minus 1 is 5. So the derivative at 2, or the slope of the tangent line at 2, is 5. So in example 4, it says to find the derivative of x squared at some number c. So I don't know what that number is, but I'm going to use the same formula. That would be the limit as x approaches that number of f of x minus f of c over x minus c. Now here I'm going to have, if I take f of x, this would be x squared. That's my function. Then if I plug in c, I'm going to plug in c and I'm going to square it, and I'll have minus c squared over x minus c. And then I can factor the top. And that would be x plus c and x minus c over x minus c. Okay, again, this is just a generic formula. And if I cancel here, I have the limit x approaches c of x plus c. Now if I plug in c for x, this is going to be c plus c, which would be 2c. So what this means is anytime I have an x squared, no matter at what point I am looking at, if I'm looking at x is 5, I plug it in and the slope is going to be 10. If I have x is 2.2, I plug it in and it's going to be 4.4. If I have this x value is 1, then I plug it in and that's going to be 2. So no matter what value I'm looking at on that point, the derivative or the slope of the tangent line is going to be 2 times that x value. Okay, so this is the general form for any x squared function. Next one. We've talked about, and this is a lot of definitions here at the top, the average rate of change would be between 2 points, which is a secant line. If I'm looking for the instantaneous rate of change, This is at one point. Instantaneous means now, or at just one point. And that is a tangent line, which is the same thing as a derivative. Now, we don't just look at this in terms of mathematical simplifying and plug and chug. We can look at this in terms of a physics problem. And here it says we have a volume of a right circular cone of height of 6, and the radius is in R. So we want to know, how is the volume changing compared to what the radius is. So first thing I'm going to do here is it says if R is changing, find the instantaneous rate of change, which is the derivative of the volume with respect to the radius. So the radius change, how does the volume change? So we want to find the derivative of the volume. Now remember, that's just V prime of the volume at some radius. And here it says the radius is 3. I'm finding the derivative of this function. Okay, I plug in 6 here. A third of 6 is 2. 2 times pi r squared. This is the function. So I have V of r, which is the volume with respect to the radius, minus the volume at 3 over r minus 3. This is the same formula. We're just, instead of f of x, we have the function is the volume, and the independent variable that's changing is r. So what's the function v of r? It's right here. 2 pi r squared minus v of 3. Now I need to plug in 3 here. So I have 3 squared is 9. And 9 times 2 is 18. So if I plug in v into the function, I get 18. So this is, or 18 pi. And on the bottom I have r minus 3. All right, so again, if I were to plug in 3 here, I get a 0 on the denominator. So I need to factor and cancel. So here it looks like I can take out a 2 pi on the top. And then I have r squared minus 9 over r minus 3. This is looking pretty good because now I can factor my r squared minus 9. So I have the limit as x approaches 3 of 2 pi times r plus 3 and r minus 3. I almost wrote an x here. R minus 3, I can cancel. And now if I just plug in 3 here, I have 3 plus 3 is 9 times 2 is 18 pi. Whoops. 3 plus 3 is 6 times 2 is 12 pi. That just didn't sound right. So I have 12 pi. So what that means is when the radius is 3, the volume is changing by 12 pi. All right, so this is just an example of how you might use this in a physics situation. And we're going to do a little bit more practice with rates of change, instantaneous and average rates of change. But other than this is it. And this was our last lesson for this year.